We're going to look at integration using partial fractions next. And I'm going to start by talking about partial fractions. So I'm going to take a little bit of a back step. Some of you may have already seen this, some of you may not have, so I want to make sure we're all kind of clear. So let's start by motivating this idea. And let's say we had 3 over x plus 2 plus 5 over x minus 1. And let's say we wanted to add these, right? What is this? Well, we know how this works, right? We've known this since probably, what, 3rd grade or something? We have to get a common denominator. And so we'd say, well, 3, that's missing the x minus 1. The 5 is missing the x plus 2. And the new denominator would be x plus 2, x minus 1, the common denominator. And so then we'd multiply out, so we'd have 3x and 5x, that'd give us 8x. Negative 3 and positive 10 would be a 7. And it would be over, we can multiply that out if we wanted to. We don't need to because it's nicely factored. And it doesn't simplify if we multiply it out, but we'd get here, right? And just to see what it looked like if we multiplied it out, let's just do that because that'll set me up in my next step. And so we'd have 8x plus 7 over x squared plus x minus 2. And that would be our fraction. Easy enough. We've done that, like I said, for years. But let's think about if I were to try to integrate this. 8x plus 7 over x squared plus x minus 2 dx. Well, this is a problem, right? If we think about what we've used to simplify fractions before, one thing we've tried is we've tried dividing. We can't do that in this case because the numerator is a lesser degree than the denominator. We've tried to use substitution. I take the more complex function, this thing right here, the derivative of this would be 4x plus 1. That's not going to in any way match up with this, even if we're to try and factor. And so I'm kind of stuck there. But notice what we started with, right? We know that this fraction here is really equal to the integral of 3 over x plus 2 plus 5 over x minus 1. Well, both of those things can be integrated very easily. We would have a 3 natural log of x plus absolute value of x plus 2 plus 5 times the natural log of the absolute value of x minus 1 plus our c. So if we can take those more complex fractions and break them down into their more simple components, what they were before they were ever added, subtracted, that would be easier. That would make our integration easier. Now this one was very easy because we were the ones that put it together, so we know exactly how it broke apart. But let's say we didn't know where we started. So let's take x over x squared plus 2x minus 3 dx. So I look at this thing and I don't know what it was before it was added together. I don't have those initial two sums. And so we need to figure out what they are. So the first thing we're going to do is we're going to do some partial fraction decomposition. I'm going to ignore the integral for just a second. I'm going to take this fraction and I want to break it down into two different fractions. Now, can I break it down? Is that always a guarantee? No, it's not. When will I be able to break it down? When the denominator factors. Can I factor this denominator? Yes, I can. The factors are x plus 3 and x minus 1. So because the denominator factors, I can break this up into partial fractions. Partial fractions, we're always looking to break up the denominator into its factors. And so the question is, what's in the numerator of both of these things? I don't know. So I'm just going to call it a and b. They're just placeholders because I don't know what numbers were supposed to be there like I did on this first one. I knew there was supposed to be a 3, I knew there was supposed to be a 5, great. But here I don't know. So to figure this out, I'm going to put it back together. This seems kind of counterproductive, but I want to put it back together so I can figure out what it looks like. So the a would be being multiplied by an x minus 1. The b would be multiplied by the x plus 3. And so we'd have an ax plus a bx minus an a plus a 3b over the common denominator of x plus 3 times x minus 1, which is the x squared plus 2x minus 3. That is equal to this thing right here, right? This is still true. So if we compare numerators, because we know the denominators are the same, if we compare the numerators, we have some x terms and we have some constant terms. There is a 1x on the left-hand side. On the right-hand side, we have an a plus bx. We have the 1x over on the left-hand side. We have the a plus bx on the right-hand side. If we think about the constant terms, the things without the variables, well, on the right-hand side, there was nothing, 0. On the left-hand side, there was a negative a plus 3b. Well, now we have a system of equations. We have a number of ways we can solve this: substitution, elimination, write it as a matrix, turn it into a matrix, and then solve it using a matrix. Any of those would work. It looks pretty easy for elimination right now. I'm just going to add these two things together. 1 is equal to 4b, and so b is equal to 1/4. And so we still need to get the a, so I'm going to plug it back into that first equation. Just looks to be a little bit easier. A plus 1/4 is equal to 1, so a is equal to 3/4. So now what I can do is I can come back up here and set up this integral in terms of its partial fractions. The a we said was 3/4, so 3 over 4 x plus 3. The b was 1/4, and we still have our dx back there. And we find our antiderivative, 3/4 natural log of the absolute value of x plus 3 plus the 1/4 natural log of the absolute value of x minus 1. Of course, we need a plus c because this is an indefinite integral. If it was a definite integral, we would just plug in at this point, but there is our answer. Let's take a look at another one. Let's say we have the integral 4x squared minus 5x minus 15 over x times x plus 1 times x minus 5 dx. Same idea as the last one. We have this really complex fraction. We can now actually see what its factors are. It's given us the factors, which makes it a little bit easier. But I don't know what the different fractions are that were added together to get here. So let's take this and let's write it as those separate fractions. So I'm going to write my a over my first factor of x, my b over my x plus 1, and my c over my x minus 5. Right, so now if I were to look at what it is when I put together, the a has to be multiplied by an x plus 1 and an x minus 5. The b has to be multiplied by the x and the x minus 5. And the c has to be multiplied by the x and by the x plus 1. And it's all over the common denominator of x times x plus 1 times x minus 5. And so let's clean up that numerator a little bit. A would be multiplied by the x squared. We'd have a negative 5 plus 1 would be a negative 4x minus 5. The b would be multiplied by an x squared minus 5x. And then the c would be multiplied by an x squared plus x. And it's all over that common denominator. And so now we can compare it to what we had in the numerator. I'm just going to recopy that so I have it right next to it. 4x squared minus 5x minus 15 times, or on the bottom, x times x plus 1, x minus 5. All right. In the last example, I went ahead and just multiplied out the a's, the b's, and the c's. I don't need to do that. I think it's actually more obvious when I leave it factored out because I can see that we have an x squared term here, here, and here. So those are all the b's, the a's, b's, and the c's. So the x squared terms would be 4 on the left-hand side, a plus b plus c on the right-hand side. On the left-hand side, our x term is a negative 5. On the right-hand side, we'd have a negative 4a, negative 5b, and a 6, a c, just a c, sorry, just the one x back there. And then the constant on the left, we have negative 15, right, we have negative 5a, and that's it. These had x terms in them both. So right away we can get the a, makes it easier. A is equal to 3. So I can replace the a's in these two initial equations and go ahead and get b and c by themselves. So taking that 3, subtracting it over, 1 would be equal to b plus c. Here we'd have negative 12, add that over, that'd be a 7. It's negative 5b plus c. So I'm going to subtract to eliminate. So I'd have negative 6 equals 6b, and the c's are gone. And so b is equal to a negative 1. And now it should be pretty easy to figure out my c. C would be equal to 2. All right, so now I just got to remember those and put them back in. So our integral, our a was 3 over x. The b was the negative 1. So you can just pull that negative to the front if you want to make it a little bit easier, and then the c was the 2. So 2 over x minus 5 dx. And so that is what that initial integral is equal to. That is our initial integral. And now we can take the antiderivative of these very easily. 3 natural log of the absolute value of x minus the natural log of the absolute value of x plus 1 plus 2 natural log of the absolute value of x minus 5 plus the c. So there's our answer. Let's take another example. Let's say we have the integral of x over x plus 1 squared dx. All right, so let's start by doing our partial fraction decomposition. And let's think about our factors. We have a factor of x plus 1, and then we have it squared, but what does that mean that we need to be adding together? Definitely have to add a couple things together, because that's what we've been doing, but a lot of times in class I'll ask the question, what should be, and I'll get the answer of x plus 1 plus x plus 1. Think about if you had the same denominator right away. They're both x plus 1s. The common denominator would just be x plus 1. We don't need the squared. So the only way we're going to have the squared there is if one of these has a square. Think about if I gave you the fraction 1/4. What things had to be added or subtracted from one another to get 1/4? Well, you can't just say the factors of 4 are 2, so 1/2 and another 1/2 in some way are going to be added, subtracted to get to 1/4. That's not going to be true because the common denominator is 2. We'd never change from that. One of them could have been a half, but one of them needed to be at least something over 4. And so 1/2 minus 1/4 gives us 1/4. But notice the common denominator was the greatest number of times that factor occurred. So we need the x plus 1 squared as well. So the a is missing in x plus 1. The b is missing nothing. It already had the common denominator. And so if we compare that to the left-hand side, our x terms, on the left-hand side we had a 1x, and on the right-hand side we had an ax. Our constant, we had a 0 on the left-hand side, we had an a plus a b on the right-hand side. Well, if a is positive 1, that means b has to be a negative 1. And so now we can express this integral. I'll draw my little arrow. It's cleaner to do this if you spread it out a little bit more, but just for the sake of being able to see all my work on one screen. Now I can write this as 1 over x plus 1 minus 1 over x plus 1 squared dx. And so if we look at this, the first one, very easy to find the antiderivative of that. That would be the natural log of the absolute value of x plus 1. Notice the second one is not the natural log because it has a power. If you wanted to do some u substitution, let u equal to x plus 1, that would be fine. It'd be 1 over u squared. Or we can think about just having a simple chain rule here. We have an x plus 1 to the negative 1 power, which would mean this needs to be a plus. Because if we're to take the derivative of x plus 1 to the negative 1, multiply the negative to the front, and then that exponent goes up to a 2, that's where we're getting the square from. And then we have our plus c. And there's our answer.